Our next speaker is going to be Scott Demyan. He's with OSU. He's a School of Earth and Natural Resources soil scientist, talking about soil carbon stabilization and permanence. So, Scott.
Thank you for the introduction, and thank you, Rafiq, for the invitation to speak today. I've seen the advertisement for this conference for many years now, but this is the first time I've actually come to it. So it was a good excuse to make the trip up. And yeah, glad to join you this morning. And I'm going to talk a bit about soil carbon stabilization and permanence. And Dr. Dick did a great job introducing some of these foundational concepts. And I'll also be talking about the no-till plots, also showing some additional data on that. So I don't have to talk as much about the background. Yeah, so today just want to talk about these concepts of soil organic carbon stability and permanence. So what does it mean kind of conceptually, and also talk a bit about soil carbon saturation, how we might measure and assess this, as many things in the soil. The really interesting thing about soil, at least to me, is how it varies over the landscape, but also the complexity in it, and the biological, chemical, mineralogical, physical aspects of it. And so the same kind of it goes to here to soil carbon stabilization and permanence and some of those uncertainties associated with it. I won't talk too much about carbon markets, but just some of the implications of management on that. Yeah, so we might start out with the basic question: why do soils store carbon? Why is there any carbon in soils? You might say that, well, it's like asking, why is the sky blue? Of course, there's carbon in the soil, but kind of at the basic level. So carbon inputs, and if we think of the time period of soil formation, so I'm kind of a pedologist by training, so sometimes I think of the scale of thousands or hundreds of thousands or millions of years. So we take the case of Ohio here. So where Ada was, obviously it was glaciated up until the end of the Wisconsin glacial epoch, and so those soils, the deposits of glacial till and the other things, they would have started out with basically zero soil organic carbon, and then over time building up. And this buildup basically was done through inputs of plant residues broken down by microorganisms. And some of that obviously was respired to the atmosphere, and some of it was stored in the soil. So during this buildup period, so anyway, during the buildup period, well, that's okay. I'll just point with my hands. So during the buildup period, carbon's increasing quite rapidly, and then it reaches a equilibrium at some point where carbon inputs are basically equaling carbon losses. And so if we think kind of on the general thing, to divide this up into environmental factors, why are soils storing carbon more so than other soils, breaking it down into environmental and pedogenic effects. So environmental, one can be wetness. So this is one of our muck soils from Logan County. This one has water at about 12 inches or so. So these continuously wet soils that build up under different vegetations, these extensive deposits, in this case, 20 or 30 or 20 or 30 inches of muck in this case, basically that those deposits of plant residues, they didn't break down over time. They were minimally processed by microorganisms because it was in anoxic conditions due to the high water table. So if we think of these environmental impacts, also we can think of cold. So microorganisms are less active when it's cold out, particularly if it's below zero. Since water is in a solid state, then we have potentially also this buildup of carbon. This is an example of a permafrost soil that's been developed in a high mountain area. So there's enough vegetative inputs here. So this is in a proglacial area. So outside of active glaciation, a bit higher up, but there's enough plant inputs during the growing season, and then these basically are minimally broken down over time. Now, obviously, if this permafrost thaws further, and actually this area did have thawing permafrost this carbon is then basically more available for microorganisms and probably lost over time. But you can see here both in this case and in our previous example here, extremely high amounts of organic carbon, but these are kind of due to specific environmental controls. All right, so if we come to our non-frozen, non-kind of wetland soils, so all of our other soils, which most of them we use for agriculture, obviously. So these still have organic carbon. This is a picture up in Wood County. One of the soils formed on sand dunes up there, and this particular pit here is at adjacent to a cemetery. So as much as the records indicate, hasn't been plowed ever. And you can see the accumulation of organic matter. It's mostly at the surface there, but even going down about 12 to 14 inches. So even in this extremely sandy soil, it's well drained. There's still this buildup of organic carbon. And then we might ask ourselves, why is this carbon here? Why is not all of it utilized by microorganisms? So this is where we get to talk about our stabilization mechanism. So chemical recalcitrance, occlusion in aggregates, and association with mineral surfaces. And so each of these, depending on the soil type, obviously, and some of these site conditions are going to vary. Just a bit about each one of these. So chemical recalcitrance is related to the basically the chemical quality of the plant and or microbial residue that's there. Some organic compounds can be readily utilized by microorganisms, whereas others are more stable. Occlusion within aggregates, so both our small aggregate sizes, those can include both recent plant residues and other organic matter, so that they're basically closed off. And then finally, association with mineral surfaces. So this is our clay minerals, also our aluminum and iron oxides that can form very strong bonds with soil organic matter. So again, depending on the soil, obviously the sandy soil has a very low clay percentage, maybe just 1 to 3%. And so that's association with clay minerals is probably very low in this soil. Also, aggregate stabilization in the soils is relatively low. So looking at some of these definitions, so stabilization, just resistance of organic carbon from being lost from the soil system. And we can consider different time frames, but particularly on the longer time frame. Permanence, then, the duration at which sequestered carbon remains in either biomass, if you're talking about forest biomass or other things, and or stored in the soil. And then something related to how much the kind of an upper limit on how much a specific soil can store, this idea of saturation. So the theoretical upper limit of a soil to store carbon due to the sum of those 3 stabilization mechanisms. All right, so something you may have heard about, I read about it quite often, is this kind of dichotomy, particular organic matter and mineral-associated organic matter. So when we're interested in soil health, soil quality, also carbon credits, we measure total organic carbon in the soil. And to get a maybe a bit more detailed picture of what's going on in the soil system, we might further measure additional fractions or pools of soil organic carbon. And these are 2 examples that I'll be expanding on a bit more. So particular organic matter, this is generally more composed of crop residues, roots, and partial state of decomposition. So this part of the soil organic matter has little mineral content. Also, a decent portion of it is relatively labile. The other side of that coin is the mineral-associated organic matter. So these are residues. The organic matter there is basically been highly processed by the microbial biomass. It might also be microbial residues, and these are either included in aggregates and or associated with mineral surfaces. So we think of this continuum here, even though it's kind of two different pools, our stability increasing this way and our stability decreasing in that way there. So if we look back in history, and there was this paper by Sanderman in 2017. So him and his authors estimated the amount of soil carbon lost since the start of agriculture. So going back to 10,000 BC, I think it's pretty amazing that they were even able to estimate any type of amount lost. But anyway, of course, using assumptions with climate, also land use, other things, and kind of starting values. But they estimated around a loss of 130 petagrams of carbon, and you can kind of see there we had this general loss for about 1500, 1800 years, going back to around 2000 years ago. But you can see then with the advent here of modern agriculture and also the expanding of it, most of the carbon loss has kind of been focused there. And so as you probably heard other places, we've lost a lot of carbon in these areas, both in grazing land and cropland. And so looking at coming a bit more recently, there's been initiatives mainly at the regional level, but then also at national level to measure what's going on, not at experiment stations, which everything's controlled, and we have our nice plots laid out, but both on farm and kind of in across the landscape. And so this is just a collection of some initiatives. Typically, they're covering anywhere from 20 to 50 years or so, and these are mainly sampling cropland areas, but also looking at forest land and in some cases grassland. And you can see most are in Europe, so climate is not exactly the same as Ohio, but getting pretty close here. So some of these areas are intense agricultural areas, and you can see kind of a range anywhere from 0.4% annual change over this period to, in some cases, a loss of 0.5 up to 1.3%. So these values are kind of show a wide range. Some of the studies, there was actually no change. And there's probably different factors for why there was this change. Some of them being practices that were prevalent in these regions, other things. For example, some of the areas also had peat soils, and so there's many factors there. So basically, this shows that many cases our soils are not at that equilibrium level. In some cases, they might be losing carbon, which is obviously bad for soil health and for climate change, but also means that we can do something about it. So now I want to talk a bit about how to measure and or estimate these different stabilization mechanisms. So looking at kind of this dichotomy of our particulate organic matter and our mineral-associated organic matter, in this case, separating out by density. We can also do it by size, which I'll talk about in a minute. But so we can separate out, take a soil sample, dry it down like we do for many of our analyses, and then using a special liquid, we can mix up different densities. So if you remember, water has a density of 1 gram per cubic centimeter, and if you have fresh crop residue, some of that residue might actually float on the surface of water, so it has a very low density. As it decomposes and becomes more associated with the organic matter with mineral phases, it becomes heavier. Yeah, and you can see here kind of the different domains in here. Lower density, we have more undecomposed plant residue. Some of it's associated with clays, but not very much. And then we move into this middle density here, which is kind of a mixture. And the higher densities here, it's majority mineral associated. All right, so who of you all have seen the movie Oppenheimer? Just one person? I was expecting a few more. I haven't seen it myself, so but anyway, so as soil scientists, we employ kind of a range of methods to look at well, everything in the soil, but also soil carbon. And one of those is using 14C. This is the radioactive isotope of carbon. And during atomic bomb testing, especially when it was atmospheric, you can see the reaction there, but basically this recreated, basically showered the whole Earth in different radioisotopes. One of those was 14C. And so over time, you can see before the mid 1940s here, delta 14C. So this is the 14C concentration in atmospheric CO2 is is below zero there. And then we have this quite large spike here during the atmospheric testing phase. So basically this showered the whole Earth in 14C. And for scientists, that's kind of a kind of an unexpected happenstance from this testing. Basically, this 14C is in the atmosphere. The plants take up that CO2. Some of that's incorporated into the soil, and then we can use it as a natural tracing experiment. And if you think of organic artifacts and other things, 14C is often used to date that. And the same can be used for soil organic matter. The only issue with that per sample, it's quite expensive, so ranging in cost from several $100s. So if you want to do a lot of samples, it's kind of quite expensive. All right, so we have two other isotopes of carbon. So one of those is 13C. So this is the so 12C is our most abundant carbon isotope, I think around 90, greater than 90%. Some of the carbon isotopes are carbon-13, which is a stable isotope, so it's not radioactive. And kind of the nice thing here is that depending on the plant type, we have this group of C3 plants, actually majority of plants. These have a 13C value of around minus 27 here. And some of our warm season grasses, for example, or in corn, their 13C value is around minus 13. So we can potentially use this also as a marker in the soil to see how fast where carbon is being incorporated in, and basically use this change here. So in the case of Ohio, oftentimes we had broadleaf forests, and most of the vegetation also in the understory was mainly C3 plants. Additionally, if we had sites that after clearance, it was mostly cereal crops grown, these would have also been C3 crops. So then if we follow and plant corn there, and if we plant continuous corn, then we have the shift from a 13C value of minus 26 to minus 13 here. And so over time, that minus 26 carbon, or the C3 carbon, it's going to decompose and be replaced with C4 or negative 13C carbon. So where do we have this situation at, or pretty close to it? Our long-term no-till experiments, particularly in the ones that have been continuous corn since the beginning, the continuous corn rotation. So Dr. Dick did a great job introducing the experiment, so I won't have to talk about too much about those. Just wanted to add that in this particular experiment here, we used a fractionation procedure, so separating out different densities from these different sampling points, depths here, so 0 to 7.5, 7.5 to 15, and 15 to 30, and then measured not only the carbon in those fractions, but also the 12C and 13C values. And this is just what the density fractionation is. So basically, we created a density gradient here in a test tube. So at the top there, the density is around 1.3, and at the bottom, it's around 2.8 here. So once we put our soil in here, some of it floats up to whatever density it is, and the other that's at heavier density, it will sink to the appropriate densities there. And then we took basically a pipette to pipette out at different depths there, corresponding to different densities. All right, and then after measuring organic carbon and the 12C, 13C signature, and with a little bit of an isotope mixing model, we're able to estimate both the original native C3 carbon and also the new, since 1962, corn contribution to those fractions at those three different depths there. So this was our lightest density, so 1.65 to 2. So this is basically all of the low density and a bit into this middle density here. So it's mainly particulate organic matter. And so you can see here, if we look at the old carbon, the C3, there's not a huge difference going down in the profile. The big difference that we see is in the surface, 0 to 7.5 centimeters under no-till. There's quite a bit of, there's a significantly increase in the C4 or the corn carbon, which is not exactly super surprising. We can see here at the 15 to 30, we have the reverse. So under plow till, we have more corn carbon incorporated. And so this these samples were taken in 2012, so that's after 50 years under this experiment. All right, so we move further here into the mesodensity. So this is getting more mineral associated. You can see here there's, interestingly, and maybe as we would expect, as we go down on the profile, our total amounts are increasing as we go from the surface to the depth. But we also have in the surface here, 0 to 7.5, we have a significant increase of corn carbon under no-till. So this is basically showing that that corn carbon's going in this light fraction here, but also into this meso density, this middle density here. So indicating that it's proceeding in being stabilized. All right, so we go to the heaviest density fraction. So these should be further stabilized in this 2.41 to 2.54 gram per cubic centimeter. You can see there's a strong increase in both plow till and no-till as we go deeper in the soil profile. So this one's dominated by the older carbon, which is again not surprising, but really not any treatment differences. In the slightly heavier density here, there's not as big of a gradient from the surface to the subsurface, but you can see under no-till, again, we have more corn carbon or more new carbon going into that fraction there. So indicating, again, there's there's further stabilization of that carbon. Yeah, so that was basically looking at one time point at Hoytville. So in a more recent study, a master student of mine, Ashley Dick, we sampled up at Worcester. I think we sampled all three rotations, but just focusing on the corn, and coarse soybean rotation here. And we applied a slightly different technique here, but this one we measured over time, so we were able to secure archive samples from some of these previous samplings, and again measured 12C and 13C. And so this one, regardless of the rotation, so average across both corn and corn soybean rotations, we found out that no-till increased the mineral associated organic carbon 50% relative to the plow till in the 0 to 15 depth. So again, indicating that that carbon under no-till, it's not just in particulate organic matter, it's not only in the labile portion, but it's being stabilized further in with mineral surfaces. And so this is important if we think of kind of the upper limit of carbon saturation or the upper limit of stability. This is the paper here from 2022 that I wasn't involved with, but is pretty interesting. So they estimated basically the upper amount of mineral associated carbon that could be stored in the soil just using the clay and silt content. And so the main differences that you see here are low activity clay soils, so dominated by kaolinite, gibbsite, and quartz. They're about 50% lower in their stabilization potential compared to our high activity soils, so smectite, vermiculite, illite, and chlorite. And so kind of from this concept here, wherever your soil kind of falls along this continuum here. So if you're currently your mineral associated organic carbon is over here on the low end, and this is the amount of the change in carbon inputs that it takes to increase that, you can see the slope of the line here is quite steep. So again, just in the case of soil organic carbon, those soils are going to increase more rapidly the mineral associated organic carbon compared to if you're up at this spot here, reaching the plateau there. So this has implications for which soils you're targeting for kind of management interventions and looking to increase not only soil organic carbon, but the mineral associated organic matter. Right, I think I'm about at the end of time, but just wanted to thank my collaborators, also Dr. Dick and Dr. Van Doorn and Triplet that started and maintained the no-till experiments over all these years. They're really a natural treasure and need to be maintained into the future. Thank you.